Now let's consider how we can deal with the ionic species contribution quantitatively, not qualitatively. So far, we learned, although we add inert ionic species, hmm, the it affects solution, the compound solubility, and also affect the equilibrium constant. Okay, but how do we treat? Not qualitatively, but quantitatively. So, in this sense, we introduce a very important concept of ionic strength. The symbol is mu. Okay, it defines. It is defined by this equation. Okay, mu equals 1/2 and multiplied by this one. Okay, Ci is the concentration. C means concentration, and Z means charge. Okay, why charge is squared? Because if you don't square, there are always positive and negative charges. So this term may be zero. Okay, to avoid zero, right? So the charge is squared. So you add all the ions contribution. Okay, and in short, you can write it this way. So here is a example. Okay? Let's calculate the ionic strength. Okay? There are three examples. Okay, first one is 0.10 molar sodium nitrate. Okay, very simple. You simply follow this equation. Okay, mu equals 1/2 multiplied by sodium ion concentration. So sodium nitrate completely dissociates in water. So leaving only sodium ion and nitrate ion. There is no sodium nitrate. Okay? So sodium ion concentration is the same as zero point 0.1, and nitrate ion has the same concentration. Okay, and their charges are all +1 or -1. Okay, so if you calculate, and then you got mu of 0.10 molar. Okay, and also unit of ion strength unit is molar. Okay, same as uh, the molarity. Okay, yeah. Likewise, you calculate this sodium sulfate. Okay, here when it is completely also dissociates in water, but when sodium sulfate dissociates, and then it leaves uh, two sodium ions and one sulfate ion. Okay, so since the concentration is 0.01 molar, right? After dissociation, sodium ion concentration becomes twice, okay? 0.02. Okay, but still the sulfate ion concentration is same as the molar concentration. Okay, so you calculate here, then you got mu of 0.03 molar. Okay, although um, this concentration is 0.01, but ion strength is 3 times larger than the molar concentration because of this one. More sodium ions are produced. Okay, and also this one. Uh, this question C is a little bit complicated, but simple. Okay? There are two species, potassium bromide and sodium sulfate. Okay, so this each individual ions contribute to ionic strength. Okay, so you calculate, you take individual ions into account. Okay, here from the definition of this ionic strength, you write it this way. Yeah. And potassium ion concentration is same as this one molar concentration. Okay, and bromide also same, but here sodium sulfate, yeah? Sodium ion concentration is twice this molar concentration, so 0.02. Okay? And after calculation you got this one 0.05 molar ionic strength. Okay, so computing mu, okay, is not simple due to ion pairing. So far we didn't consider any ion pairing. Okay, for example, this one magnesium sulfate. Okay, you know, it may dissociate into magnesium ion and sulfate ion, and in addition to that, uh, magnesium sulfate itself can be dissolved in water, yeah, in this form, magnesium sulfate. This is aqueous means this is aqueous species. This is completely soluble. Okay, yeah. So we have to consider the ion pairing effect. Okay, this is a very common phenomenon in aqueous solution. Okay, salts with ions of charge more than 2 are not fully dissociated because they are highly charged. So ionic pairing phenomenon becomes uh, much stronger. Okay, yeah. This is the example. In 0.025 molar magnesium sulfate, they are highly charged. Magnesium and sulfate ions are divalent, okay, plus 2 and minus 2. So in this case, 35% of magnesium ion is bound in the ion pair. Okay, this percentage is actually very high. Okay, so we can write the equilibrium constant for ion pair formation. Okay, the concept is the same. This is ion pair equation. So plus n valent positive ion now makes ion pairing with here n negative charged this one L anion, okay, and makes this ion pair, and by definition this equilibrium constant is given by this one. Okay, here uh, this gamma one, gamma, you see gamma in this equation. This gamma is called activity coefficient. Okay, you will see shortly. Okay, and this table shows the percentage of um, metal ion bound as ion pair in 0.025 formula. This is the same as molarity to ml solution. Okay, here are two positive ions, okay, sodium and magnesium ions, and two anions, chloride and sulfate. Okay, and so the combination is 4: sodium chloride, sodium sulfate, magnesium chloride, and magnesium sulfate. Okay, you see this percentage is the ion pair percentage. Okay, in aqueous solution, as you see, as the charges increase, the more ion pair percentage there. Okay, here the smallest one is what? Sodium chloride. Yeah, sodium is only plus 1, it takes plus 1, and chloride minus 1. So ion pairing percentage is only 0.6%. Okay, but one of them is highly charged, like sodium sulfate. Sulfate takes divalent. Okay, so ion pairing percentage becomes 4% increased. Okay, likewise magnesium chloride, in this case the ion pairing percentage is 8%. Okay, so here we can say the higher concentration, the higher ionic charge, the more ion pairing. All right, so here in this case 0.025 formol magnesium sulfate. Okay, here in this case magnesium sulfate, the free magnesium ion concentration is 0.016 molar, right? But if there is no ion pairing effect, what is the concentration of magnesium ion? This one 0.025 molar, okay? Because this one completely dissociates. Likewise, sulfate ion concentration free. sulfate ion is the same as magnesium ion, and this one magnesium sulfate. This is ion pairing species. Takes 0.009 molar. So if you add this concentration and this one, and then you can get 0.025 molar. Okay, and this one 0.009 molar is about 35% out of 0.025 molar. Okay, now we introduce very important concept, which is activity and activity coefficient. Okay, activity is defined as this equation. Okay, activity A of species C equals molar concentration, this one, multiplied by gamma. Gamma is called activity coefficient. Okay, why we introduce activity coefficient? That's because with only molar concentration we cannot explain this um, the behavior of solubility or equilibrium constant change, okay, as the ion strength increases. Okay, so to explain more accurately, we use activity and activity coefficient. So from now on, yeah, for a while, we use activity instead of this molar concentration. Okay, the unit is the same since this molar concentration unit is a molar, yeah. So this one activity also has a unit of m, large M, molar concentration. So this gamma activity coefficient, the unit is no, there is no unit for only number, okay, for activity coefficient. Okay. So for this reaction, we rewrite the equilibrium constant using not concentration, not molar concentration. So if you rewrite the equilibrium constant using activity, and then we can write using molar concentration and activity coefficient. Okay, now this is a more accurate calculation of equilibrium constant. Okay, but here at lower um, ionic strength, which means that there are not many ion species in solution. Okay, the activity, the coefficient approaches unity. This unity is 1. Okay, and this equilibrium constant approaches concentrate uh, concentration K. This one. Okay, this equilibrium constant uh, approaches this one. Well, I'm sorry, this one TMDC is a thermodynamic. Yeah, yeah, you see. So at the lower ion strength, this activity coefficient becomes also approaches unity, and thermodynamic equilibrium constant K approaches concentration equilibrium constant K. Okay, so actually this is thermodynamic equilibrium constant we have to obtain, but how do you obtain this one, thermodynamic equilibrium constant? One way to measure this one, thermodynamic equilibrium constant, uh, you can do it rather easily. Measure concentration equilibrium constant at several lower ionic strengths, okay, and extrapolate to 0 mu. At 0 mu, at 0 ionic strength, this is thermodynamic equilibrium constant becomes same as the concentration equilibrium constant. Okay, and for the case P, yeah, now the using activity is a more accurate expression. Okay, in this case, molecular iodate, right? Using activity, and it can be translated into concentration and activity coefficient. Okay, but now another question we meet, okay, which is the how do we calculate this activity coefficient? Yeah? Okay, we understand, the more accurate calculation is to use activity, but to calculate activity, we have to know this activity coefficient. Okay, there is a very famous theory which is called Debye-Hückel equation. Okay, Debye-Hückel equation. They um, derived the expression for activity coefficient. You see this equation. And this is when I look at the original paper for this one, that paper is too complicated. It's not easy at all. There are so many equations and the derivation. Okay, so simply we accept this equation as fact. Okay, log gamma equals this one. Okay, minus 0.51 z squared multiplied by square root of ion strength and divide by 1 plus parenthesis alpha square root mu divided by 305, okay, at 25 degrees C. Here alpha is the ion size, but unit is picometer. Okay, yeah, don't forget that. This alpha is ion size, hydrated ion size, not pure, ion size. Okay, hydrated ion size. Okay, this table uh, gives you um, the ion size of um, a lot of species, different species. Mostly they are all ions. Okay, as a function of ionic strength. Okay, this is this one. This first column here. This is the hydrated ion size. As you see, for proton, hydrogen ion, this hydrated ion size is 900 picometer, right? Actually, this proton is the smallest ion, right? But in aqueous solution, it is hydrated. The ion size becomes larger, quite larger, okay? And it's 900, okay? So actually, it cannot be 900 exactly. But this value. These values are approximate values, okay? Yeah. For example, there is a second law. This ion size is 800, not exactly 800, around 800, okay? And this activity coefficient, look at that as a function of ionic strength, okay? From the low ionic strength and the higher ionic strength, from 0.001, okay, 0.001 to 0.01, okay? At the lower concentration, gamma value becomes approaches 1, although it is smaller than 1. All right, yeah, like that. Okay, yeah. Okay. So we can simply say this activity coefficient at very low ion strength, it approaches 1. Okay? And you simply take a look, yeah? And higher ion strength, this gamma value becomes smaller and smaller. Okay, these ions all the monovalent ions, right? But what about this divalent and trivalent and even tetravalent? Okay, as the ionic charge increases, um, this gamma value decreases very rapidly. Okay, for example, this magnesium and beryllium ions, right? The ion size is around 800 picometers, and at the same under the same concentration, 0.001 molar, right? The ion activity coefficient is only 0.872. But here, monovalent ion, it is very close to unity, right? So here we know that this activity coefficient quite depends on the what? Not ion size, but depends on the charges, ionic charges. All right. So for the trivalent ions, right, the effect is much higher. Okay, here at the same concentration, okay, it is 0.738. Okay, much decreased. And the extreme case, which is the tetravalent species, the effect is even uh, higher. All right, yeah. This is a table. So when the problem is given, and then you can find uh, the activity coefficient from these tables. Okay, or if you remember this one, this equation, and then you can use this equation to get this activity coefficient. Okay, here once again, uh, take a look this equation. The alpha, as I said, this is the um, hydrated effective hydrated ion size, okay, in picometer. Okay, yeah. This equation, however, works well when ionic strength is smaller, less than 0.1 molar. Okay, for the solution whose ionic strength is higher than this one, 0.1 molar, you have to use another, the theory. Okay, you see soon, and look at this one. This figure shows how this activity coefficient depends on the ionic strength. Okay, depending on this monovalent, divalent, trivalent, or tetravalent. Okay, as you see, for the monovalent ions, ionic strength, activity coefficient start from 1 and it decreases rather slowly. Okay, but for the higher valent ionic species, uh, the ionic activity coefficient more rapidly decreases. Okay, this one for tetravalent species is so severe. All right. So here we can say effect of ion strength and charges and ion size on gamma. Okay, as ion strength increases, gamma decreases. As charge increases, gamma departs more from unity. And for the ion size alpha, the rest is small. The dependence is not very big. Okay, the smaller ion size, the more important activity effect it become. Okay, here you see the smaller ion. Okay, and this one. So the dependence of activity coefficient on ion strength. Okay, and it, it depends. Yeah, it decreases. But here, as ion size, you know, decreases, the ionic the activity coefficient decrease uh, is more rapid. Okay, you see. From 900 picometer to 50 picometers. Okay, at a certain ionic strength. Yeah, for example, at 0.001 molar, it the decrease is not very prominent. But as ionic strength becomes larger, for example, 0.1 molar, okay, the larger ions, the ionic active coefficient is only is 0.83, but for the smaller ions, active coefficient becomes smaller. Okay, yeah, that's the general trend. Okay, so using the tables, we can find this one, the ionic the activity coefficient. Okay, for a given concentration. Here, for example, let's consider 3.3 millimolar mercury mercurous nitrates. Okay, it dissociates completely. Okay? By definition, we can write this ionic strength is 1/2 multiplied by mercurous ion concentration, since and multiplied by 2 squared. Okay, because it has takes plus 2. charge, okay, and nitrate, and then -1 squared, okay, and this one, ion strength is after calculation it, it is 0.01 molar, okay, so this question is made this way, okay, by purpose, and the question is activity coefficient of calcium ion, okay, so ion strength is 0.01 molar, and then from here you look at the calcium, okay, calcium here, and ion strength is 0.01, and then you find this one, this value 0.675, yeah, this is the activity coefficient for calcium, okay, in this solution, okay, yeah, this is not very difficult, okay, but what if when you have different ion strengths, okay, and then we can use a technique called interpolation, okay, interpolation. This technique is used when the two values, and if you don't know, if we want to know uh, the unknown value, and then you find that just next to true data here, okay, in this case you want to know the y value for x16 here, okay, and then if you know the y values for x is 10 and 20, okay, when x is 10, y value is 0.67, when x is 20, and y value is 0.83, but you want to know the y value when x equals 16. So assuming, yeah, in this small range the changes, the y value changes linearly, okay, linearly, and then you get this value, okay, the y value for this one. Because the slope is the same, you can write this equation from here. Unknown y interval here divided by delta y equals unknown x interval here divided by delta x, okay, and here, let's take these two, okay, or this one, y is 0.83 here, 83, and then you don't know this one, this is y, and divide by this one, x is equal to 20, and this one is 16 here, okay, and delta y is uh, for this one 0.83 here and 0.67, okay, and the difference here is 20 minus 10, okay. Using this equation we can get y, which is now 0.766, okay. This is the technique of interpolation, yeah? And use these values from the table, and then you get the middle points, okay? And here is an example. Calculate activated coefficient of proton when mu equals 0.025, okay, 0.025. From the table you know this mu value is in between mu of 0.01 and 0.05, okay. I will show you, yeah? Okay, this one, in this case, okay, since your case is that mu of 0.025, in between these two, okay, and we know the gamma, we read from the table at 0.01 of mu, and then gamma value is 0.914, and for 0.05 mu, and gamma is 0.86, okay. Using this equation we can get this one, okay, gamma at 0.025, okay, which is calculated to be 0.894, okay. And then you can check the validity of this value using the theory. Okay, using this Debye-Hückel theory, you can calculate, yeah, the activity coefficient for proton. Yeah, the proton hydrated effective radius is 900 picometer. Okay, and then log gamma you calculate to be minus 0.054. Okay, and then take if you calculate gamma here, then you got finally 0.881 and compare. There is some discrepancies. Okay, but this discrepancy is inevitable. Theory is not the perfect, and also the table is not perfect. Okay, so this difference is inevitable. Okay, so you can, depending on your situation, okay, you can use this one, this value or this value. Okay, it's up to you. But what about the activity coefficient of a non-ionic compound? Yeah, non-ionic compound. In other words, if there is no charge on the species. Okay, so since there is no charge, but for these neutral molecules, activity coefficient is almost 1. Okay, almost 1 here. Okay, 1. But what about gas? Okay, for gas, we can define the the same. Uh, we can consider the same concept. Okay, in gas phase, the activity can be defined by this pressure multiplied by activity. Okay, coefficient. All right. But in this case, activity of gas species is called by different name, which is a fugacity. Okay, fugacity. In this case, the activity coefficient is called fugacity coefficient. All right. For gas at or lower 1 bar, this fugacity coefficient is almost 1. Okay. For the gas species, activity is almost the same as the pressure. Okay. I think that's because in gas species, gas state, all the gas molecules are quite they are set apart. Yeah? So the activity pH coefficient is almost 1. Okay, but what about the at high ionic strengths? But in this case, we don't meet actually the very high ionic strengths. All right, activity coefficient in concentrated salt solution are not the same as those in dilute solution. Okay, yeah. You see, look at this the figure first. When activity ionic strength increases, activity coefficient of, in this case, proton decreases. Okay, this part only Debye-Hückel theory explains only this part, and then as mu increases, it decreases, and then it passes through this minimum and then keep increasing. Okay, this one, this part, especially at higher ionic strengths. The behavior of activity coefficient cannot be explained by Debye-Hückel theory. Yeah, you need a quite a different theory. Okay, that's quite beyond the undergraduate course. Okay, yeah. At high ionic strength, activity increases with ionic strength. All right.